Hi AP Chem and happy brand new packet. The good news about the start of this packet with equilibrium is that this was the mini unit that we did earlier in the year. You've already learned the basis of equilibrium, and you also know about equilibrium and balance just from being alive. If you look at the picture on the front of the packet, which I included, I have to still put that copy of the front page on because it was Cars last time. It was Lightning McQueen. And this time, it's this elephant and this monkey on a teeter-totter, and you gotta take a second and appreciate the cuteness of it. It drips cute, but the point is, they were looking for balance and there is no balance. Right now, nothing's gonna change though. That elephant end is staying down and the monkey end is staying up. This is still not going to change with time. So that's why I put that on there to get you thinking about which way reactions go, and that an equilibrium reaction doesn't necessarily imply equal amounts on both sides. Think about that. A chemical equilibrium is opposing chemical reactions, A and B, that proceed at equal rates. That's the idea for today. Today's notes are easy. I think today's notes are easy. Reactions forward, reaction reverse. Proceeding at equal rates. Equal rates. Not frozen in time in this case, unlike the monkey and the elephant. This is like the day in class when I was like, okay, well, if somebody walks in, somebody's going to have to walk out, and that's equilibrium. And right on cue, Scotty walked in to eat the old food. One of you would have had to walk out. So if there are 9 of us in a room, and one person walks in, one person walks out. A different person can walk in and Scotty can then walk out as long as there are 9 in the room. If one person goes in, somebody has to go out, and that's equilibrium. The dynamic equilibrium I'm talking about is an equilibrium that changes like that, where Scotty walks in and somebody walks out. That's dynamic, keeping the room at 9 but not the same 9. There is definitely equilibrium. That reaction has stopped on the front of your packet, but it's a static equilibrium. The elephant flopped, it outweighs the monkey, the end. I should have had my dog in this video to be the elephant. She's pretty close. So what we're looking at today is the concept of equilibrium, with the big take-home message being, for equilibrium to exist, forward and reverse reaction rates are equal. But the amount of stuff on each side doesn't have to be equal as long as the exchange rates are. So at equilibrium, concentrations do not change. So if I have 1 molar of A and 2 molar of B, it's going to stay the same at equilibrium. There are going to be molecules changing from A to B and B to A, but it's going to be at a rate that keeps those concentrations equal. The system needs to be closed for equilibrium to happen, because if I'm making the product, if I'm making B and just keep taking it out, A is just going to keep making B. We're not going to reach an equilibrium in an open system. So we need a closed system, and this also only occurs in reactions that are reversible. If A just makes B with 1 arrow, A isn't going to go back to A, so I'm not going to be looking at an equilibrium. I'm going to be looking at the standard reactants make product. So I've got my double-headed arrow there, and we talk in terms of equilibrium about both forward and reverse reactions, where a forward reaction is A making B, and the reverse reaction being B making A. We read left to right naturally, so we count that as the forward reaction. Could I have written this as B yields A with the equilibrium arrow in between? Yes. In that case, B would have been my forward and A would have been my reverse. It's not a thing which way I write it, because it is a reversible reaction. Most of the reactions we've seen so far this year have not been. They've not been equilibrium reactions, but this is. Here it is again by definition of an equilibrium reaction. There it is, rate R and rate F, forward and reverse. If my forward rate equals my reverse rate, my reaction rates are equal, but pay attention, my rate constants don't have to be equal. Rate constant does that weird molarity per second thing. So if one side were unimolecular and one were first order and one were second order, I'd have a different K for each side, but the rates could still be equal. So your rate constants aren't equal, but your rates are. Try this. If A again is 0.1 molar and be 0.2, my rate constants couldn't be the same, because then my equilibrium would not exist. So my quotient of my rate constants, if I divide them, and my ratio of participants will be constant. If I'm always at equilibrium, I'm always going to have the same ratio of A to B. My rate constants will be the same ratio too, even with a change in temperature. So there you go. Again, the equilibrium is dynamic, means we're freely moving back and forth from A to B. You don't need to know the rate constant info, except that the rate constants aren't equal, but the rates themselves are. And if you look at your rate equation with K times concentration, that should make sense. Is it most accurate to say there's no change in products or reactants? Nah. No change in the concentration is more accurate. Because again, it doesn't have to be the same people. Really, in the example with Scotty, where Scotty walked in and one person walked out, it could be that day when the bowling team stampedes in and 8 of them come in and all 8 of you get sick of them and walk out. The number of people in the room didn't change, but none of you started out in there except me, and you left me with them, and they're ripping apart the cooler and knocking over the desks, and things are happening, and you're done. But it's still an equilibrium, and then if they leave, you can come back. It's safe then. The takeaway points from this lecture: changing concentration. At equilibrium, the concentrations of reactants and products no longer change with time. 0.1 and 0.2, we're stuck. We're good. For equilibrium to occur, neither products nor reactants can escape. That's the same thing as saying it's in a closed system, and a particular ratio of concentration terms equals a constant. So that's what that means. You're always going to have the same ratio. So if I've got 1 molar and 2 molar, I could have 2 molar and 4 molar. I could have 20 and 40. The ratio will be the same, and I stop, no matter what. At equilibrium, when equilibrium is reached, the reaction stops net movement, but not the change in individual molecules. So, again, sort of free flow with that. But the concentrations don't change. Rates are equal. Rate constants do not have to be. Concentrations do not have to be. The only guarantee I've got you is that rates are equal at equilibrium. You've only got one practice problem today, and I don't think it's too bad. I'll put up the answer tomorrow, or next time, and there you go. Intro to equilibrium.